So today I'm going to be talking about the physics concept of projectile motion and give a little background information on what it is, as well as going over how to solve a problem dealing with projectile motion because it can be a bit tricky, but if you know your basic physics concepts and kinematic equations, you should be fine. So to start off, what is a projectile motion? Well, a projectile is basically an object where the only force acting upon it is gravity. So if you were to throw a baseball, it wouldn't be a projectile motion until it left your hand. So if we were to draw a free body diagram, it would look something like this. Now there are two different types of projectiles we're going to be talking about, horizontal projectiles and angled projectiles. So a horizontal projection is where it has an initial horizontal velocity and would look something like this, where the initial height should be higher than its final height. And something important to keep in mind when working with the horizontal portion of projectiles is that when an object is in horizontal motion, the acceleration of the object will be 0. This means that the velocity will remain constant as well, and the initial velocity will be equal to the final velocity. Now, of course, the object will only be in horizontal motion towards the beginning of its descent, and with gravity, it will maintain a vertical motion. So in solving things such as time or distance, we can split up the motion of the projectiles into two different tables, one being horizontal and one being vertical. Both tables will consist of the initial velocity, the final velocity, change in position, acceleration, and time. This just helps to organize the information we know and what equations we can plug it into to find the missing distance, time, etc. Now, something very important to know is that when splitting the horizontal and vertical motions of the projectile, the only variable you can intermix with each other is time. This will make more sense once we work out a problem. Now, on the other hand, vertical projectiles are a little more complicated because when solving, you have to do one extra step in the beginning because now the object is being projected at an angle, and we have to use sine and cosine for finding the initial velocities of both the horizontal and vertical portions. For example, kicking a soccer ball. And a crucial difference between this and horizontal projectiles is that the initial height is also the final height, because it goes up and then it comes back down. So if you split the object's path of motion in half, the first half and the second half should be a reflection of the other. Therefore, when solving, you can make it easier and only solve for one half and then double it to find the distance and time as a whole. Now in solving, you're going to do the same thing and make a horizontal and vertical table of variables just to help organize your information to help solve the question. Now that we know more about what projectiles are, let's go on to working out some problems and bringing together what we just talked about and applying these tactics. So let's start off with a horizontal projectile motion. A golfer practicing on a range with an elevated tee 4.9 meters above the fairway is able to strike a ball so that it leaves the club with a horizontal velocity of 20 meters per second. And we can assume the acceleration due to gravity is 9.8 meters per second, and the effects of air resistance can be ignored. So the question is, what horizontal distance will the ball travel before striking the fairway? Now let's start off by drawing our two tables of horizontal and vertical variables. So let's start with what we know for the horizontal variables. Well, we know that the ball leaves the club with a horizontal velocity of 20 meters per second. So that's the initial velocity. And as we mentioned earlier, because it has a zero acceleration, its initial and end velocity remain constant, so we can put the final velocity at 20 meters per second as well. And now we need to find the distance the ball travels until it reaches the ground, but we don't know how long it takes either. So we're going to leave this blank for now and see if filling out the vertical variables table will help us. So now for our vertical table. The initial velocity will be 0 because it starts with horizontal motion, which is independent from the vertical variables of motion. Now we don't know what the final velocity is, but we do know the change in y, which is the height of the tee, which is 4.9 meters. Now for acceleration, just to make things simpler, we'll say that going down is the positive direction. So therefore, the acceleration of the object will be positive 9.8 meters per second. And now we don't know the time either, which is what we need to find. So looking at the variables we have here, we can see that our second kinematics equation, where the change in y is equal to the initial velocity times the time plus 1/2 times the acceleration times time squared. Now we know that our initial velocity is 0, and anything multiplied by 0 is 0, so we can take out the first half of our equation, leaving the change in y equal to 1/2 times the acceleration times time squared. But we're trying to find time, so we can change our equation to time equals the square root of 2 times the change in y over the acceleration. And now we can begin to plug in our variables. Our acceleration is 9.8 meters per second, and our change in y is 4.9. And by using a calculator, we get that the time is equal to 1 second. Now, as I had mentioned previously, the only variable that can be intermixed between the horizontal and vertical tables is time. So we can place this time over on the horizontal table as well and use it to help solve for the change in x. And in this case, we can use a simpler equation. So velocity is equal to the change in x over time. And we want x by itself, so we can change the equation to the change of x is equal to velocity times time. And when we plug in our variables and solve in our calculators, we get 20 meters. And that is the horizontal distance the ball will travel before striking the fairway. So now onto our angled projectile motion problem. So a ball is launched by a device at ground level with an initial velocity of 28 meters per second at an angle of 30 degrees to the horizontal. How far does the ball travel before reuniting with the ground? So now before we draw our horizontal and vertical tables, we have to do one extra step. So to make things easier, let's draw out this scenario. We have a ball being launched at ground level at a 30-degree angle going 28 meters per second in a vertical direction. So now we're going to use sine and cosine to help find the initial velocities of both the horizontal and vertical parts of motion. Now to find the initial velocity in the x direction, you will use cosine because it deals with the hypotenuse and adjacent side to the angle, which is 30 degrees. So you will multiply the given velocity of 28 meters per second by the cosine of 30 degrees and you get 24.25 meters per second. And this is your initial velocity in the horizontal direction. And for the vertical initial velocity, you do the same thing but use sine because this deals with the hypotenuse and opposite side of 30 degrees. So you will multiply 28 meters per second by the sine of 30 degrees, and this gives the initial velocity in the vertical direction, which is 14 meters per second. So now we can move on to solving the actual question. And let's redraw this scenario to help us picture what's going on. So because this is an angled projectile, the object will be projected into the air from a certain height, in this case the ground, and come back down. And at the highest point is where the velocity of the object will be 0. Okay, now to make things easier, let's split this projection right down the middle. And by working with just one side and then doubling the time, we can solve for the whole projection as a whole. So let's focus on the first half, and we can choose the up direction as being the positive y direction. And now let's draw our tables. Let's start with the vertical variables this time. So we know that our initial velocity is 14 meters per second because of the work we did here previously. And because we split it into half, at the highest point of the object's motion, the final velocity will be 0. We don't know the change in y or the time it takes the object to go up, but we do know that the acceleration is negative 9.8 meters per second because we already said the up direction is the positive y direction. Looking at these variables, however, there is a way to find the time it takes the object to go up. And it's by using our first kinematics equation, which states that the final velocity is equal to the initial velocity plus acceleration times time. Now, once again, we want to solve for time, so we can change the equation to time equals the final velocity minus the initial velocity all over acceleration. Now, if we plug in our variables and solve, we should get 1.43 seconds as our time. But remember, this is only half of our whole projectile, so we're going to multiply it by 2 and we get 2.86 seconds. And like before, time being the only variable we can intermix between the horizontal and vertical variables, we can place this time on the horizontal table. So let's fill out the rest of this table. We know from the previous work we did here that the initial velocity will be 24.25 meters per second, and that because with the horizontal motion the acceleration is 0, the velocity doesn't change, so the final velocity will be 24.25 meters per second. We need to find the change in x. The acceleration we know is 0, and we know the time from solving it from the vertical table. So in order to solve for x, we can use the simple equation for velocity, which is that velocity is equal to the change in x over time. We want to solve for x, so we can change the equation to the change of x equals velocity times time. And when we plug in these values and solve, we get 69.355 meters, which is the distance the ball travels before reuniting with the ground.